Hello guys, can you hear me well? Okay, I guess that you must be able to hear me now. Yes, I can see myself. Okay, how are you doing guys? It's so nice to see you again here. And I hope that we can have a great stream today as well. Nice. Today we're gonna continue talking about number theory. We're gonna go more deeply into details, and we're gonna cover some more advanced topics like power, Fermat theorem, little Fermat theorem, and combination. Salam Aura. And you don't need any prior knowledge to attend this topic stream. I tried to find a way to explain everything so that you can understand everything even without knowing any prior knowledge, including the previous live stream. Even without knowing what was discussed in the previous topic stream, you can understand what we're going to talk about today. Though it's good if you watch all the streams that we have had already, they have their own topics that it is very good for you to know them as well. So without any further ado, I guess we can now start talking about our topics today. Shall we start? Are you guys ready? Number theory is very important in competitive programming at all, in ICPC, in IUI, in everything. Number theory is one of the most important topics, so it's really important for you to know the topics that we're gonna discuss in number theory. Yes, we will talk about Mohs algorithm as well in the future topic streams. And this is the link to all the topic streams that we have. You can see them here. We're going to cover everything from dynamic programming, graph algorithms, number theory, and every other topic that is helpful for you. Each week we have a topic stream, and we hope that after a while we will be able to cover every important topic that you need to know. Thank you very much. I'm so happy if I can have a good impact in your learning. That's my main goal. It makes me so happy if I'm able to do that. Okay, nice. So let's start talking about the topics that we have today. So the first thing that I want to discuss today, as discussed before, there's some issue with this. The first topic that we want to talk about today is power or exponentiation. Assume that we want to calculate a to the power of b. What can we do in order to do that? What is your suggestion? And guys, there might be some noise today here. Let me know if it was bothering you. I mean, if you hear anything. Yes, as you said, the first idea is to multiply a b times. So the first thing that we can say, the first thing that comes to our mind is to multiply a. Let me make this bigger. It's to multiply a b times. So what we can do, the first thing that comes to our mind is this. We can define an answer that is initially equal to 1, and we can say that, let's write better. We can have an ans equal to 1 initially, and we can have a 4 I int I equal to 0 or 1, I less than or equal to b, I plus plus, or we could say I equal to 0, I less than b. Ans equal to ans times b. So this would work, and sometimes, because ans can be very huge, the value that you will have as your answer can be very huge. Sometimes what we do is that we calculate it modulo some mod, as you have seen before, because otherwise we might have overflow. So if we do that, we can have a modulo mod, and because we might have some overflow to an integer as well, mod is something that fits into an integer. So ans, your ans will be always at most mod. Your b is also your ans is less than mod, so it fits into an integer. Your b also fits in an integer, but the product of two integers might not fit into an integer. So the product must be first saved in a long, so you should multiply 1 by it, so that everything will be first calculated as longs, so that you're sure that you don't have any overflow, and then you calculate it modulo mod. So this way you can calculate a to the power of b. This is ans times a. Okay. So this is the first idea that comes to our mind. This is the naive approach, the first idea that comes to our mind in order to calculate a to the power of b. It would work if, for example, your b is up to, for example, 10 to the power of 6, and you're calculating this power only once. This way it would work. But there are, so is it clear so far? This trivial approach to calculate power? If it is, please use emoji or put a plus in the comments. This emoji or put a plus in the chat. So it wasn't very complicated. The only point was that sometimes we want to calculate it modulo some mod. And the point is that when we are calculating modulo some mod, in order to make sure that everything is okay, we don't have any overflow, to be safe, we multiply them as longs. Because this is an integer, the product of two integers might be a long. It might not fit into an integer. For example, assume that this is 10 to the power around 10 to the power of 9, and this is also around 10 to the power of 9. To be safe, that's the when we have the product of two integers, in order to be safe, we calculate them in a long. And in order to calculate them in a long, we can just simply multiply 1 at the beginning. 1 does not change anything. But when we save 1 this is a 1 that is saved as a long. So first, this 1 will be multiplied by ans. So it remains ans, but it will become an ans that is a long. So you are multiplying a long by an int. C++ automatically calculates it as a long. So we have it then. After multiplying 1 by ans, you will have an ans in long, and then when you multiply that ans by a, again the product will be saved in a long. So far you will have a long which is ans times a. You're sure that you don't have overflow. Then you calculated modulo mod. So now again it is an int. I mean it fits into an int. It is still a long, but it also fits in an int, because mod is, for example, 10 to the power of 9 plus 7. It's something that fits into an integer. And now that it is small enough, you cannot save it in ans, which is an int. This way, so this, I mean what you will have here, this is gonna be a long, but it is small enough. It is small enough to be saved in an int, in an integer. So it's okay. Ans is an integer. You first define it as an integer. So now you can save it in ans and it will fit there. I mean, there won't be any issue. Exactly. When you calculate the product of a long and ints, it will be saved in a long. Okay. We will talk about this. And long plus ints, no, long plus ints will be also a long. I mean, that's all. When you calculate two things, I mean any operation, product, addition, anything, when one of them is long, one of them is in an integer, C++ automatically calculates the result in a long. So when you have any operation between a long and an integer, it is product, add, division, subtraction, anything. The result will be stored in a long. So temporarily, this will be saved in a long. I mean, this value is calculated as long, but it is going to be small enough when you calculate it modulo mod. So when it is small enough, you can save it in ans. Okay. So is this, I didn't change it, sorry. Is this clear? So this is going to be small enough to be saved in an integer, and then you can save it in ans. Okay. So everything clear so far? I mean, if you don't have any question, we can now talk about how can we calculate it in a faster way. Assume that your value of b is now up to, for example, 10 to the 9. Assume that a and b are both up to 10 to the power of 9. Or they can be even more than that. They can even be up to 10 to the power of 18. That is also possible. Now we can talk about that. How can we do that? Well, a is not important if it is up to 10 to the power of 18, because your mod will fit into, for example, assume that your mod is 10 to the power of 9 plus 7. Your mod is never too large. Your mod always fits in an integer. Always in competitive programming problems, when they give you a mod, they give you a mod around 10 to the power of 9. They will not give you a mod around 10 to the power of 18. Because the point is that when your mod is around 10 to the power of 18, then you cannot do anything. You cannot product two numbers that are up to 10 to the power of 18. Because that won't fit even in long. You should consider even larger types that they cover a wider range of numbers. So the point is that your mod is always 10 to the power of 9 plus 7. So whatever a is, a modulo mod is important. So a, you can always assume that a is up to 10 to the power of 9, but b can also be up to 10 to the power of 18. Okay, so for your a, you can always assume that a is up to 10 to the power of 9, a is less than mod, and for b, you can even assume that it is 10 to the power of 18. That is also possible. So now let's see that what can we do in this way. There is a very important thing that we can say when you're calculating, when you're calculating a to the power of b, there are two cases. Either b is even or b is odd. We can say a very important fact that looks trivial, but it helps you a lot. I mean, this is very trivial, but it helps you a lot in order to calculate power. So the point is that a to the power of b, when b is even, is gonna just be a to the power of b half times a to the power of b half. Right? So a to the power of b, when b is an even number, is just a to the power of b half times a to the power of b half. And when b is odd, a to the power of b is gonna be a to the power of b minus 1 half, or the floor of b half, times a to the power of b minus 1 half times a itself. So it will be the product of these three numbers. a to the power of b minus 1 half. It's not b minus 1 half, it's b minus 1 half. Okay, let me write it this way to make it more clear. B minus 1 is an even number, so when we calculate the product of these two numbers, it's going to be a to the power of b minus 1, and then when you multiply it by a, it's going to be a to the power of b. So so we see that we can relate it to some number, I mean to some b around b half. So it gives us some hope that maybe we can just calculate it in O of log or something like that. How can we do that? So the main idea is to use this fact. This is very trivial, yet extremely useful. Extremely useful. When a to the power of b is a to the power of b half times a to the power of b half, when b is even, and it's equal to a to the power of b minus 1 half times a to the power of b minus 1 half times a, when b is odd. So the point is that when you calculate the product of two numbers, you can just implement it like this. Instead of having a 4 as much as b, I mean start from 1 and go to b, we can just write a function, right, int of power, int of, let's name it pw. It gets two integers, int a and int b, and returns a to the power of b to you. So what you can do in here is this. You can say that first you always need a base case. You always need, I mean, this recursion, I mean always when you have recursion. For example, in order to calculate a to the power of b, you are using a to the power of b half. When you have recursion, let me write it here. When you have recursion, you'll always need a base case. I mean some case that works as your base. I mean when you get here, you're done and you know the answer. You always need a base case when you are calculating something recursively. So what can be our base case here? When we are calculating a to the power of b, what is our base case here? Can you say that? What can be our base case? If b is equal to 0, return 1. Exactly, that's going to be great. Or b equal to 1. Yes, they are both good ideas. We can stick with the case where b is 0, for example. That might be enough. So we say that if b was 0, it's easy. I can answer it very quickly. If b was equal to 0, I can return instantly. Return 1. Instantly. Because a to the power of 0 is always 1. So in this code, we want to return a to the power of b modulo some mod. We say that if b was 0, instantly the answer is 1, return 1. Now we have our base case. Now we say that we consider the two cases that we were talking about. B is even or b is odd. First, consider that b is even. Well, first let me write it in a way that might be a bit problematic, and I will ask you that why it is problematic. We can say that return pw of a and b half times a to the power of b half. But this is problematic in many ways. Can you say that why it is problematic? Exactly. So the main point is this, that if you write it like this, your PW will be called twice. Okay, so the point is that you have a to the power of b, and then you're going to use a to the power of b half. You call it twice. I mean, once in here, and once in here, you will call it. But the answer will not change. You're just calling it twice. And again, each one of them will call a to the power of b twice as well. So this way you will have a lot of calls that you didn't really need. And this way you're going to have a lot of calls, and this way you cannot achieve log. Because if you want to achieve log, you need to call a to the power of b half exactly once, and a to the power of b4, for example, exactly once, and so on. You need to call them exactly once. When you do it like this, when you call them like this, there would be a lot of recursion. And that might be bad for you, because your time complexity will not be in O of log anymore. You are calling a to the power of b half twice, and a to the power of b four times, a to the power of b eight times, and so on. And we can show that it's going to be O of b at the end. At the end, the number of function calls will be O of b, which is not good, because if we wanted O of b, we could just have a 4 and calculate a to the power of b. So we will never do this. And also there was another small issue that I wanted you to say, that we have to also calculate mod, and we have to multiply it by 1 LL at the beginning, because this might not fit into an integer. This is an integer, but their product can be a long. So temporarily we need to keep everything in a long. And then when we calculated modulo mod, then we're safe. Then now it is an integer, and we can easily return it as an integer. So in order to fix this problematic code, we don't want to call it twice. So as you mentioned, what we can do is to just store it in a variable. Yes, it would be O of b if we call it twice. Yes. It can be shown that it will be O of b, and if we wanted O of b, we could just simply have a 4. When b is up to 10 to the power of 18, we do not want to have O of b. Or when it is up to 10 to the power of 9. And do not forget that if it is up to 10 to the power of 9, b can be used as an integer. If it is up to 10 to the power of 18, you need to define it as a long. Or in short, I write LL. I mean, wherever I write LL, I mean long. You need to write long in your code instead of LL. Or if you have type def of long, or something like that, then you can use long. If you write LL, if you use LL without writing anything, you will have a compilation error. So you need to either write long in here, or you have to use type def or define or something like that, if you know what they are. So whenever I write LL, I mean long. So when b is up to 10 to the power of 18, I have to use LL of b. Now I say that instead of calling a to the power of b half twice, I just save it in a variable. I know that it fits into an integer because it's a to the power of b half modulo mod. Between type def, define, or using, it's better if you do not use define. It's better if you use type def instead of define or using, because type def is specific for defining types, but define is more general, and type def has its own benefits. But because it's not our main discussion right now, I will move on to continue talking about power. Yeah, sure. Yes, it is some sort of it's like memorization somehow. I mean, we will save it. We will save that. in a variable like p, we will say that what is pw of a and b have. This way I'm sure that I will call it once because this value will not change. I mean, why should I calculate it twice from the beginning? When you calculate it once, you know its value. So you can multiply it by itself. You do not need to calculate it once again from the beginning. And then just return 1 LL times P modulo mod. And that's all. When it is even. I calculate A and B half and I calculate the product of P by P. The other case, I can just write else. It means that B modulo 2 is 1. This is the odd case. So in the odd case, I just need to define P again, very similar to the previous case. It is PW of A and B minus 1 half. And then I say that I need to multiply the P by itself and then by A as well. And do not forget that instead of B minus 1 half, I could use B half in here as well, because C++ automatically calculates the floor of B half, which is equal to B minus 1 half. So even if you write B half, there wouldn't be any issue. So you can just say that in this case, return 1LL times P again. When you multiply two numbers, calculate it modulo mod. I mean, just write modulo mod. So that you are sure that again is in an integer, and then multiply it by the third number. I mean, when you're multiplying three numbers, when you multiply three integers, they might not even fit in long. When you multiply three integers, they might not even fit into long anymore. So you need to make sure that whenever you multiply two numbers, then you calculate modulo mod, so you're sure that it again fits into an integer. So the point is that again in here we have some number that fits in an integer, and then we're multiplying by an integer again, and then we say modulo mod. And this way power can be calculated. So as our base case, we only said that when B is 0, we return 1. If B is even, we return A and power of A and B half times itself. If it is odd, we multiply an A at the end to it as well. Okay, so for example, assume that we are calculating something like 3 to the power of 7. The point is that when you calculate 3 to the power of 7 with this code, it will call 3 to the power of 3, and whatever the answer is, I mean, for example, assume that it is equal to some A. In here we will return A times 3. So A times A is going to be 3 to the power of 6, and when you multiply it by 3, it's going to be 3 to the power of 7. And 3 to the power of 7 will be calculated using 3 to the power of 1. For example, if it is B, and B is equal to 3, because 3 to the power of 1 is going to be 3. In here, you will calculate B times 3. And then this itself, 3 to the power of 1 itself, uses 3 to the power of 0. So 3 to the power of 0, if it is C, in here we return C times 3. And we know that in here we have a base case, so we do not call anything. We will instantly return 0. So we will continue until we reach our base case. When we reach our base case, we're done. We will return, and everything will be calculated this way. And the point is that because each time this power is divided by half, I mean each time that we have a new call, our power will be divided by half, by 2. So after log of B calls, b becomes 0, and for 0 the answer will be easily calculated, and we will go back and everything will be calculated from that. So it means that we solved exponentiation in of log. I'm not sure if I wrote it properly, but this is gonna be how it works. Is it clear? Let me make sure that so this is how we can calculate the a to the power of b in O of log. If it is clear, please use the emoji or write a plus in the chat. So yes, by doing it, it will be calculated in O of log n. Okay, nice. So this is gonna help you a lot when you calculate exponentiation. I mean, I was writing it previously. Now it is correct. So this is how we can calculate a to the power of b in O of log of b. Okay. And this will be very helpful because sometimes b can be very large, and we cannot have a 4 to b. That's going to be a lot of computations. Instead, we're going to calculate everything in O of log of b. And this way, everything can be calculated easily. And we can have a to the power of b. Okay, now that we know this, let's see a CF problem and see how can we solve it. How can we use this knowledge to solve a problem on Codeforces? Let's talk about this problem, 359C prime number. Let me send it here. So the problem is saying that assume that you have a prime number x and an array of integers a1, a2 to an. Okay, and then calculate this number 1 over x to the power of a1. So you have a prime number x and your array of non-negative integers is a1, a2 to an. You calculate 1 over x to the power of a1 plus 1 over x to the power of a2 plus 2a1 over x to the power of a sub n. You write this number on a piece of paper, and then you will sum up these fractions to a common denominator and sum them up. And assume that you got a fraction like s over t, and your t is going to be x to the power of a1 plus a2 plus 2an. Well, the point is that your denominator could be better than this. Your denominator could be smaller than this if you just calculate the LCM of all the denominators. So the point is that now that your denominator is this, you want to see that what is the GCD of s and t so that you can reduce your fraction. So now you want to reduce the resulting fraction. I mean, when you have a fraction s over t, if they are common divisors, you can divide both of them by that common divisor and write your fraction in a simpler form. You can write your fraction in a form that's the GCD of s and t is going to be 1. So the point is that you calculate this number and you write the denominator as x to the power of a1 plus a2 to a, and now you want to see that what is the greatest common divisor of s and t. And if it is x to the power of something, I mean you have to write that what that x to the power of something is. For example, in here, let's see the first example. Let me write it here. For example, in here, your x is 2, and you have two numbers, a1 and a2. Your fraction is going to be 1 over 2 to the power of 2 plus 1 over 2 to the power of 2. Because it is 1 over x to the power of a1 plus 1 over x to the power of a2 and so on. So this is your fraction. If you write it in a way that your denominator is going to be 2 to the power of a1 plus a2, your denominator is going to be 2 to the power of 4. And your numerator is going to be 2 to the power of 2 plus 2 to the power of 2. So your fraction will be equal to this. So it's going to be 8 over 16. But this fraction can be reduced. Your numerator and denominator have common divisors. Both of them are divisible by 8. The greatest common divisor is 8. So you can divide both of them by 8. So you need to say that what is the common divisor of your numerator and your denominator. Or in the second case, you're going to have, I write it very fast, 1 over 3 to the power of 1 plus 1 over 3 to the power of 2 plus 1 over 3 to the power of 3. If you write the denominator as 3 to the power of a1 plus a2 plus a3, you're going to have 3 to the power of 6 here. Your numerator is going to be 3 to the power of 5 plus 3 to the power of 4 plus 3 to the power of 3. And you can simply see that the GCD of your numerator and denominator is going to be 3 to the power of 3. So it's going to be 27. Does it make sense? If the statement is clear, please use this emoji or put a plus in the chat again. Like this. So we have a prime number x and n numbers a1, a2 to an, and you have 1 over x to the power of a1 plus 1 to the over x to the power of a2 plus 2, 1 over x to the power of an, and you write this fraction, sum them up, write them as a fraction that its denominator is x to the power of a1 plus a2 plus a3 to an, and your numerator is going to be something. Now you're going to calculate the GCD of numerator and denominator. Okay, nice. And the limits, as you can see in here, your n is up to 10 to the power of 10 to the 5th, x is up to 10 to the power of 9. And a1 to an are also up to 10 to the power of 9. So this is your number. N is up to 10 to the power of 5th. X and a are up to 10 to the power of 9. And this is your number, 1 over x to the power of a1, 1 over x to the power of a2, and so on. So let's see that how each one of these fractions will look like when we change the denominator. We're going to change the denominator to x to the power of a1 plus a2 to an. So what's the numerator that we get from the first number? I mean, when we are changing the denominator, what is the numerator that we get from our first fraction? What is going to be the numerator that we get from our first fraction? So we are changing our denominator to x to the power of a1 plus a2 to an. Exactly. The point is exactly. the power of x, I mean the first fraction, the numerator that the first fraction gives us is x. I mean the power is gonna be the sum of all the numbers other than a1. So let's say that a1 to an, let's say that it is, let's name it s. Let's name the sum of all the numbers as s. So the first number gives us x to the power of s minus a1. The second number gives us x to the power of s minus a2 and so on. The last number gives us x to the power of s minus an. So this is what we get. X to the power of s minus a1 plus x to the power of s minus a2 and so on to the end. And we know that a1 is less than or equal to a2, less than or equal to a3, and so on to an. So they are in increasing order, a1 to an. So these numbers are going to be in decreasing order. So now the point is, so that your least power, I mean your smallest number is this. So now I say that let's have a CNT for everything. Let's have CNT of I that says that in here, how many x to the power of i's do you have? How many x to the power of i's do you have in here? So for example, you have 1 x to the power of s minus a1, 1 x to the power of s minus a2, and so on. So when you are calculating CNT, you have a 4 inch I. This I is not the I that I wrote here. I less than n, I plus plus. You can just simply say that CNT of s minus ai plus plus. Because you have now 1 more x to the power of s minus ai. And s minus ai, since ai's themselves are up to 10 to the power of 9, s is going to be at most 10 to the power of 9 times 10 to the power of 5. And when you subtract ai from it, it's going to be around at most 10 to the power of 14. So it will be in a long lung. So this is a long lung. So CNT must be a map from long lung to int. So we have this CNT must be a map from long lung to int of CNT. So we save that. How many power of I do we have in our denominator? So now that we know this, the point is that the first assumption is that our GCD is going to be our minimum power. I mean, it's going to be x to the power of s minus an. Because this has the least power, ai's are in increasing order. So when we calculate s minus ai's, they will be in decreasing order. So the first assumption is that our GCD is our last one, our last number. But the point is that, let's see that, for example, let's say that this is y, this power is y. The point is that maybe we will have exactly x to the power of y's, exactly x of them. And when you sum them up, it's going to be x to the power of y plus 1. So the point is that the power might increase. Maybe you will have several powers, several elements that for all of them the power is the same. So when you sum them up, the power will be increased by 1. So the point is that what we can say is that we can say that our answer initially, our current answer, is going to be s minus a of n minus 1, which is our last number. What we can say is that while CNT of car was divisible by x, it means that you have the number of x to the power of cars that you have, the number of x to the power of cars that you have is divisible by x. When it is divisible by x, you can write a greatest power for them. I mean, you can simplify them. and they give you even greater powers. For example, in the first example, if you remember, n was 2, x was 2, and a1 and a2 were 2 as well. So what you had was 2 plus 2 to the power of 2 to the power of 2 plus 2 to the power of 2 over 2 to the power of 4. So your smallest power was 2, but you had 2 of them. So you could write 2 to the power of 3 instead of that 2 to the power of 2's. Okay, so the point is that when you have x, when the number of x to the power of cars is divisible by x, you can just replace them with x to the power of car plus 1. So what you can say is that instead you can just say that CNT of car plus 1 will be increased by CNT of car over x, because for any x to the power of cars, you can replace them with 1 x to the power of car plus 1. And then you can say that CNT of car is equal to 0 after that, or mod equal to x, which is 0. And then you can say that car plus plus. Now our answer will be 1 more than what it was before. Now our smallest power is more than what it was before. So you can say car plus plus afterwards. So this way your car will be increased until you get a point that CNT of car is not divisible by x anymore. And then that car is going to be your answer. And then you just need to calculate x to the power of that car and report it as your answer. And how much this while will take? The point is that in this while, I mean, if you consider this CNT, each time CNT of car plus 1, because x is a prime number, it is at least 2. When you do this operation, I mean, you have n numbers initially. The sum of CNTs, initially, the sum of CNTs is n. Initially, the sum of CNTs is n. But each time when you increase car, you see that CNT of car plus 1 will be added by something and CNT of car will be 0. But CNT of car plus 1 will be added by a smaller number, because it will be added by CNT of car over x. So each time in your while, your sum of CNTs will decrease, and it can never become 0. It's easy to see that it will never become 0, because you will continue as long as CNT of car is divisible by x, and you're sure that CNT of car is not 0. Initially you set it as the minimum of the minimum degree that you had, and then afterwards you know that it at least got something from its previous number, so it's not 0. So each time your sum of CNTs will decrease and it will never become 0. So this while will take at most n operations. The while will be executed at most n times. This while will be executed at most n times, so your answer will be easily calculated in of n times some log for map. So this way your answer can be easily calculated. There is an issue in here. Okay. Is it clear now? So the only point that we're going to use power is at the end, when we want to calculate x to the power of car. And how do we calculate x to the power of car? X to the power of car can be simply calculated by the exponentiation that we talked about right now. We can easily calculate x to the power of car. If the solution is clear for you, please use the plus or use this emoji. And thank you very much, others. Nice. So there are no questions, no further questions on this problem. Okay. Nice. So this is how a problem like this can be solved. We just were thinking about what is the smallest, what is the smallest degree, and we try to sum them up as much as we can group them in groups of size x and move it, increase the power. We were doing it, and at the end we will end up with some car, and that's going to be x to the power of that car is going to be our answer. Nice. So now we will move on to the next important topic that we're going to talk about today, which is Fermat-Litter theorem. Fermat, the T in the end is silent. Fermat-Litter theorem. What does this theorem say? It says a very interesting thing. It says that assume that A is a prime number. Assume that A is a prime number. We can show that, or instead of A, let's use P. P is a prime number. We can show that for any A less than P, A to the power of, for any A from 1 to P, A to the power of P minus 1 modulo P is 1. And you don't believe how useful this theorem is. This is something that looks like random. Okay, A to the power of P minus 1, we say that for any prime like P, and for any A from 1 to P minus 1, A to the power of P minus 1 modulo P is 1. This is it looks like a very random fact. That's okay. It's like some of those useless mathematical things that we just prove, and they're just hard to prove. But you don't believe that's how practical this is and how useful it is in many Codeforces problems. So let's take an example. For example, assume that let's say a prime number. Can you guys tell us a prime number? Just suggest a small prime number. It's better if it is very small. For example, Atmos 5. 17 is very huge. 2 might work, but 2 is also so small. Okay, let's just stick with 5. Good. 5 is good. For example, 5 is not very small and not very huge. For example, let's say that, for example, P is 5 and A is just a random number as well. A is like, I don't know. For example, suggest A. I want to show you that whatever you suggest, it would work. A must be from 1 to 4 when P is 5. Okay, so one suggestion is 2, one suggestion is 3. A cannot be 10. A can be from 1 to P minus 1. And then I tell you that it is okay if only it's not a multiple of P. But for now, let's just say that A is from 1 to P minus 1. One of your suggestions was 2, one of your suggestions was 3. I will show it in both of the cases. For example, first assume that A is 2, P is 5. This Litter theorem says that A to the power of P minus 1 modulo P must be 1. So what is 2 to the power of P minus 1 modulo P? 2 to the power of P minus 1, A to the power of P minus 1, or 2 to the power of 5 minus 1, in here is going to be 16, right? It's going to be 2 to the power of 4, which is 16. And you see that modulo 5, it's really 1. What about 3, p equal to 5, a equal to 3, 3 to the power of 4 minus 1, 5 minus 1, sorry. It is 81, it is 3 to the power of 4. 3 times 3 times 3 times 3. It is 81, and you see that modulo 5, it is 1. Or you also suggested a equal to 4. Let's see a to the a equal to 4 as well. 4 to the power of 5 minus 1 modulo 5. This is gonna be 4 to the power of 4, which is equal to 2 to the power of 8, which is 256, and modulo 5 is 1. So again, it's correct. And even if you use other p's, for example, assume that, as you said, p is equal to 3. If p is equal to 3, a must be either 1 or 2. So a has 2 cases. For example, a is 2. 2 to the power of 3 minus 1 modulo 3. It's going to be 4 modulo 3, which is 1. So again, it's correct. So what it says, we see that it was correct. It says that for every prime, p and every a from 1 to p minus 1, then I'll show you that it's just enough that a is not a multiple of p. Because if a is a multiple of p, if a was a multiple of p, a to the power of p minus 1 was divisible by p, because a itself is divisible by p. But a must not be divisible by p. For example, it's easy to see that a cannot be 0, a cannot be p. Because if it is a multiple of p, a to the power of p minus 1 is also a multiple of p, so it won't be 1 modulo p. But for every a from 1 to p minus 1, we can say that a to the power of p minus 1 is going to be 1 modulo p. That's the main points that we're going to prove here. You're welcome. Happy to hear that. Thank you. Yes, so exactly. So now let's see that why it is true, and then see that how it's going to be useful. As I said, it is very useful. I mean, you don't believe how useful it is, and in how many problems you're going to use this fact. I'm going to tell you a combinatorial proof for it. The combinatorial proof is very interesting. Let's say that we have a necklace. Okay. And it has some stones. For example, it has p minus 1 stones. So, or we can say that, we can also say that maybe in this way it would be easier. We have a table, or let's just stay with the necklace, that's good. So we have a necklace and it has n stones. N precious stones. N is equal to p minus 1. And each of these stones can be of one of a possible types. We have a type of stones, and we have unlimited number of them. I mean, from each type we have so many stones. So we have a necklace. It consists of, I mean, this necklace is circular and it has n stones on a circle, and each one of them can be of one of a possible types, and from each type we have unlimited stones. We can have as many stones as we want. So how many ways this necklace has? How many ways do we have for this necklace? I mean, at first we can assume that we can forget that it is a circle. I mean, we have n stones. Each one of them can be of a types, a different types for them. For each one of them, we have A types. So how many ways do we have in total in order to choose these stones when each one of them have A possible choices? No, not a factorial. No, not A factorial. Exactly, A to the power of n, or A to the power of p minus 1. So we have p minus 1 stones. The number of stones is p minus 1. Each one of them have A ways. This one can be of one of A types. This one can be of one of A types. And this one can be of one of A types. So in total, we're going to have A to the power of p minus 1 ways for that. Okay. We're going to have A to the power of p minus 1 ways in total. Do you all agree? If you agree, please put a plus or use this 100 emoji in the chat. Put either a plus or use this 100 emoji. So in total, I mean, we have n stones. Each one of them have A ways, can be of one of A possible types. So in total, we're going to have A to the power of p minus 1 possible ways. It is simple combinatorics, right? Nice. So now let's say that, let's get rid of, sorry. This sometimes happens, that my tablet crashes. Let me take it back. So we want to get rid of all the cases, get rid of the cases where all the stones are from the same type, are from the same type. So in how many ways all of the stones are from the same type? We had A to the power of p minus 1 ways in total, exactly. In A ways, all of them are from the same type. If all of them are from the same type, it means that there are A ways for them, right? So it's gonna be A to the power of p minus 1 minus A, right? Ways, minus A ways, that all of them are not from the same type. Now I want to show that this number is divisible by P. I just now see that I made a mistake. Let's say that we have P stones. Let's change this and assume that we have P stones. I want to now show that P is because P is a prime number. We have P stones. So this is gonna be n is equal to P. Sorry for that. Now I want to show that A to the power of P minus A is divisible by P. I want to show that A to the power of P minus P, A to the power of P minus A is divisible by P. Right? I want to show that this number is divisible by P. So how do I say that? I say that now consider all the cases we have. I mean, for all the necklaces, I mean the necklaces form a circle. Assume that, for example, P is 3 for a second, and for example A is 2. So for example, one way you have is this A, B, A. But do you agree that this necklace has no difference with this necklace that we have, with this necklace that we have in here A, in here also A, and in here B. Because it's on a circle, if you just rotate it, I mean, if you just rotate it a little clockwise, you will have this way. So these two necklaces are really the same. It's like you just rotated it a little bit. Also, it is going to be the same as BAA. So the point is that all of them are the same, right? Yes, it is circular symmetric, right? So the point is that when you are on a circle, you can just rotate it and you will get this one, and from this one you will get this one, from this one you will get this one, and so they are all the same. So the point is that because P is prime and you have P stones, you have exactly P stones, the point is that as you will rotate them, all of them are going to be the same. And I want to show that because P is prime, these all are going to be P different possible configurations. For example, if P was not prime, for example, if P was 4, you had a case that you had A, B, A, B. And the point is that if you rotate it once, you will get BA, BA, and if you rotate it again, you will again get AB, AB. So this group will have 2 members. But I want to show that if I find the groups that I have in here, all the groups that I have in here, I want to show that these groups will have exactly size P. The size of these groups will be exactly P. The size of the groups of circular shifts, circular rotations is exactly P. So if you consider any necklace and you say that if by rotation they become equal to each other, you consider them equal, you don't consider them different. If you can rotate them and they will be like each other, you won't consider them different. In here I want to show that if P is prime, the size of each group is P, and if I show that the size of each group is P, I have automatically shown that A to the power of P minus A is divisible by P. Because I showed that all of these ways are in groups of size P. So I showed that I have these many ways, and these ways can be grouped to groups of size P. Therefore, it shows that this is divisible by P. You have A to the power of P minus A ways, and they can be grouped in groups of size, they can be easily grouped in groups of size P. That shows that all the ways, I mean the number of ways that you have is divisible by P, right? So how can I show that? I showed that, for example, if P is not 4, it is possible that by a group have size 2. But the point is that, do you agree that each group, the size of each group should be a factor of P? I mean, for example, let's change this to X, or let's change it to N. Let's say that it is N. If we have N stones in total, and if you consider that you have rotations, and you can, if you consider that if you two ways are equal, you consider them the same way, I mean the same, you can show that the size of the group should be a factor of N. For example, here N is equal to 4. And you see that the number of groups must be either 2 or 1 or 4. It is not possible that the number of groups is going to be 3. Can anybody say why? Can anybody say that why the number of group cannot be a number that n is not divisible by that? What's the issue that way? If we have some numbers, some configurations in a group that it is not really n is not divisible by that. What is the issue with that? So the point is that if it is not, I mean, the point is that we know that if we rotate n times, we will get back to where we are right now. So if we start from here and go like this, after n times, we have to come back to where we were, right? So the point is that if the size of the group is not really, n is not really divisible by that. For example, you have these possible configurations from this one. If you rotate, you will go to here. If you rotate from here, you will go to here. If you rotate, go to here. If you rotate, go to here, and so on. After n times, you will not get back to where we were at the beginning. So the point is that for each group, the number of configurations that you have in that group must be a factor of n must be divisible by that. And now, because p was a prime number, the size of a group must be either p or it must be 1. And what is the case that it will be 1? I mean, a group will have only one possible configuration. That's the case that all of them are the same. In the case that all of them are the same, the size of a group will be 1. But if all of them are not the same, it is definitely not 1 and it's going to be p. And this way, it shows that a to the power of p minus a is going to be divisible by p. I will go more deeply in the proof of it in the next live streams. But right now, because we have more things to discuss, maybe we have to skip it faster. But there are also so many other ways to prove it as well. But this is the combinatorial proof that so far it showed that a to the power of p minus a is going to be divisible by p using just considering the number of necklaces that we're going to have. The point is that if we consider a necklace and it has p stones, each one of them are of one of the possible a times, the number of ways is going to be a to the power of p. And if you remove the cases where all of them are equal, you're going to have a to the power of p minus a, and the rest of them can be grouped into groups of size p. Therefore, a minus p, a to the power of p minus a is going to be divisible by p, which shows that a to the power of p modulo p is going to be equal to a. This shows that a to the power of p is equal to a modulo p. So the point is that when a to the power of p is equal to a modulo p, this shows that a to the power of p minus 1 is also equal to 1 modulo p. Therefore, what we were looking for is correct, and Fermat will be proved. And this is gonna be proved. I mean, it still there is a lot of things that we can move more deeply into. Then we skipped some of the parts very fast. I mean, we talked about some of the parts very fast. And we can definitely talk more about the proof of this Fermat theorem. And maybe we can even have only one session only related to Fermat theorem, and we talk about all the possible proofs, etc. on Fermat. But so far, is the intuition clear? Did you get the intuition of why a to the power of p minus 1 is equal to 1 modulo p? Yes, this proof is very interesting. And let me share a Wikipedia page with you. If you want, you can also look at this Wikipedia page that shows the proofs of Fermat theorem. It tells you many proofs for Fermat theorem, but the most interesting one is to prove this combinatorial proof. I chose to tell you this combinatorial proof because it is the most interesting one. And if you want to read more about it, you can read this resource in Wikipedia, and it explains that what is exactly the proof. Okay. So, yes, we're going to talk about how to calculate the inverse, etc. We'll talk about that. That's the next thing that we're going to talk about. So far this was about the intuition of the proof of Fermat. We can go more deeply, not only in this proof, there are also other proofs that I used to explain before, that they are also interesting, but the most interesting one is this combinatorial proof. It has the most beauty among all the possible proofs that Fermat-Little theorem has. That's why I wanted to discuss this one today. If you want to read more about that, you can read it in the resource that I shared. Now, I want to see that how this Fermat-Little theorem can be useful. I mean, how can we use it to solve a problem? And before that, also, as you guys also said, A does not really even have to be from A1 to P minus 1. A can be anything. If, for example, if A is equal to P plus 1, there's no difference with A being equal to 1. Because A can be calculated modulo P. I mean, whatever A is, you can consider A modulo P. And therefore, A can be anything other than multiples of P. Because if A is a multiple of P, A to the power of P minus 1 is gonna be equal to 0, not 1. It's not gonna be equal to 1. It's gonna be equal to 0. Otherwise, if it is not a multiple of P, A to the power of P minus 1 modulo P is gonna be 1. If A is not a multiple of P and P is a prime. Okay, yes, so I said that A also can be greater than P. There's no issue in that. A also can be greater than P, but the point is that A cannot be a multiple of P. Because even if A is equal to, for example, P plus 5, A to the power of P, I mean P plus 5, modulo to the power of everything, anyway, P plus 5 modulo P is equal to 5. So P plus 5 to the power of X is going to be equal to 5 to the power of X. Okay. And the main point is that why if A is not a multiple of P, it would not work in that proof? Because you remember this part that I skipped, and I said that because A to the power of P modulo P is A, then A to the power of P minus 1 modulo P is 1. The point is that if A is divisible by P, you cannot remove it from both sides and say that because A to the power of P modulo P was 8, then A to the power of P minus 1 modulo P was 1. But we get into those things in more detail. So for now, we just know that A to the power of P minus 1 modulo P is 1. So now let's say how this can be useful. I mean, how can we use it? Well, the point is that you sometimes you need to calculate division. You need to divide two numbers. And you cannot simply do that because everything is modulo mod. So assume that, for example, you are calculating something, you have so many computations, and your answer is currently ans. I mean, your answer is currently stored in ans variable. And the point is that because ans could be very huge, ans is calculated modulo some mod. Ans is calculated modulo some mod. Now you want to divide your ans by something. How can you do that? How can you divide your ans by something? For example, you want to divide your ans by some number x. Well, the point is that you cannot say ans divided by x like this, because this ans is not your real answer. It is your answer modulo mod, modulo the mod you have. So the point is that, for instance, assume that your answer right now is mod plus 1. And your mod is, for example, your real answer. Your real answer is mod plus 1. And your mod is, for example, 10 to the power of 9 plus 7. And you want to not divide it by 2. You want to divide it by 2. The point is that in your ans variable, what is your ans variable when your real answer is mod plus 1? When your real answer is mod plus 1, what is your ans variable then? Exactly, your ans variable is going to be 1. Your ans variable is going to be 1. So when you want to divide it by 2, when you want to divide your number by 2, for example, your number is right now 10 to the power of 9 plus 8, and this will be divided by 2. So your new answer needs to be something like this: 5 times 10 to the power of 8 plus 4. It must be something similar to this. But the point is that if you say ans divided by 2 like this, your ans will become 0. It will be nonsense. So the point is that if your answer is calculated modulo mod, you cannot simply divide it. You cannot see that how you can divide it by a number. And that would be a bit problematic. Now this is where Fermat Litter theorem will come into place and will help you to calculate a divided by b even when a is modulo mod and you don't know the real value of a. So in here the issue was that you don't know what ans really is. You just know it's modulo some mod, but you don't know what really is. That's why you will have issues in division. You can do multiplication, you can do addition, you can do subtraction, but you cannot do division this easily. So the point is that when you want to calculate, assume that a is calculated some mods, modulo some mods, modulo some mods that is given to you, and mod is a prime number. And guys, in brackets, let me tell you that this is why your mods are always prime. You see that, I mean, you might see that in Codeforces problems, your mods that are given to you are prime numbers. And you might ask that why they are always prime numbers. This is one of the most important reasons that your mods are prime numbers. Your mods are prime so that you can easily use things like Fermat. So if you just ask that why your mods are prime, the main reason is that you can use this Fermat theorem. So this Fermat theorem is that useful that the reason that you see that your mods are always prime is because of this Fermat theorem. So assume that a is calculated modulo some mod, and you want to calculate a divided by b, modulo that's mod again. But first of all, let's rewrite it in another way. A divided by B modulo mod is going to be equal to A times B to the power of minus 1. Okay, I just rewrote it in another way. A divided by B is equal to A times B to the power of minus 1. And we know that since assume that A and B are both less than what? A and B are both, for example, up to 10 to the power of 9. Mod is 10 to the power of 9 plus 7. We know that, based on Fermat, we know that B to the power of P minus 1 modulo P is 1 for every prime number P greater than B. So we know that B to the power of P minus 1 modulo P is 1 for every prime number greater than B. And we know that B is less than 1. So we can say that this modulo mod is gonna be A times B to the power of minus 1 times B to the power of mod minus 1. So what I did is that I just multiplied a B to the power of mod minus 1 to this. Why? Because I know that this is 1. So this does not change anything. I just multiplied my answer by 1. By multiplying something by 1, nothing will change. I wanted to calculate A divided by B, and then I said that, okay, multiply A divided by B to the power of mod minus 1. Nothing will change, right? Because this is 1. I mean, nothing will change by multiplying a number by 1. So the main idea is that when you want to calculate A divided by B, you can just simply multiply it by B to the power of mod minus 1 because this is 1. You can always multiply anything by something that is 1. So it does not change anything. It does not change A divided by P modulo mod, B modulo mod. Okay. And do not forget that A, we don't know what is the real value. We don't know what is the real value, and even though A itself, its real value is divisible by B, but what we have stored is not necessarily divisible by B anymore. So A is something that it is really divisible by B. Its real value is divisible by B, but because we have calculated modulo mod, it's not divisible by B in here. But it is really divisible by B. So this is really an integer. I mean, this is really an integer, but because right now, because we have A modulo mod, it won't be an integer if we divide A modulo mod by B. So the point is that A divided by B, I mean, we have A modulo P, A modulo mod. We can multiply it by B to the power of mod minus 1. And then what it is equal to? Modulo mod. It is simply equal to A times B to the power of mod minus 2. So the point is that when you have A divided by B, instead, this is the key point. Instead of dividing by B, you can multiply by B to the power of mod minus 2. That's the key points. It says that, okay, you have something, you want to divide it by 2. Don't divide it by 2. Instead, multiply it by 2 to the power of mod minus 2. You want to divide it by anything. You want to divide it by 10. Instead of that, multiply it by 10 to the power of mod minus 2. And this is the case when your real value is divisible by, for example, 10. But what you have in mod is not divisible by 10. The main point is that instead of division, you can just multiply it by that value to the power of mod minus 2. If mod is not prime, this won't work. There's something else that Fermat says when your mod is not prime. And that is related to concepts like phi, and which is more advanced in number theory. Maybe in future we will talk about that. But for now, let's just consider that your mod is a prime number. So is it clear? Yes, sure. Let's take a small example. Yes, sure. Assume that, for example, you have an answer and you know that it is divisible by 2, but you cannot divide it by 2. Why? Because you have calculated modulo mod. Assume that, for example, let's say that, for example, your mod, assume that your real answer right now, your real A, let's say it like this. Assume that your real A is 6. Your mod is 5. And you know that A is divisible by 2. You want to divide 6. You want to divide that A, which is its real value is 6, by 2. Okay, so you have a value that it is really 6, but you don't know it is really 6. You just have it modulo mod. You just have it modulo 5. So what is your variable A equal to? When its real value is 6 and your mod is 5, what can it be? What A will be equal to? Exactly, A will be equal to 1. Exactly. A is equal to 1. So you cannot just say A divided by 2. You cannot do that. This will not work. This gives you 0, which is nonsense. Because the real answer is 3. The answer that we're expecting is 3. Do you agree? Because A is really 6. And you know that the real A is divisible by these 2. But this A you have is not necessarily divisible by 2. Because the A that is saved is modulo mod that has changed. So it's not necessarily divisible by 2, which is your B in here. So it says that when you want to calculate A modulo 2, A divided by 2 modulo 5, do you agree that 2 to the power of 4 modulo 5 is 1? This is Fermat, right? This is Fermat. 2 to the power of 4 modulo 5 is 1. 2 to the power of 5 minus 1 modulo 5 is 1. So the point is that instead of calculating A divided by 2, let's calculate A divided by 2 times 2 to the power of 4. This is 1, so it does not change anything. But the point is that when you multiply it by 2 to the power of 4, it's like it says that let's calculate A by 2 to the power of 3 instead of dividing by 2. Let's see what it says. Fermat, in one word, says that instead of dividing by B, multiply by A to the power of, by B to the power of, why I said P in here? Instead of dividing by B, multiply by B to the power of mod minus 2. This is what Fermat says. Instead of dividing by B, multiply by B to the power of mod minus 2. Why? Because it said that when you want to divide by B, you can multiply by B to the power of mod minus 1, because that's 1. So you have B to the power of mod minus 1 in numerator and B in denominator, and then you can instead just have B to the power of mod minus 2. So let's see if it works. So you have A, which is equal to 1. It says that instead of dividing by 2, multiply it by 2 to the power of 3. So what is it? What is 2 to the power of 3? Instead of dividing by 2, I'm gonna multiply by 2 to the power of 3. What is 2 to the power of 3? It's 8, right? So I will multiply my 1 by 8. And what is this modulo 5? What is 1 times 8 modulo 5? Instead of dividing 1 by 2, I multiplied it by 8. It is going to be 3. And 3 is exactly what we expected. 3 is exactly what we were looking for. So it's giving us correct answer. You see? So it says that instead of dividing, even though we did not know that our A was 6, but we really calculated A divided by 2. Why? Because there was one main point. And first, we know that the real value of A is divisible by B. And then we know that A divided by B is an integer. The real A divided by B is an integer. And the point is that when you calculate A divided by B, you can multiply it by B to the power of mod minus 1, which is really 1. And then the point is that this is going to be A times B to the power of mod minus 2. So instead of dividing by B, we can multiply by B to the power of mod minus 2. Yes, it really has value. Let's take another example as well to make sure we're completely okay. Let's say that, for example, maybe we can use greater values. We cannot use very great values because let's use, for example, let's say that our A is this time 3 and our mod is 7. This is modulo mod. Sorry, B is 3. We want to divide by 3. And our real A is, for example, what do you think our real A is? What do you want to suggest something? Our real A must be divisible by 3. Our real A, good, is 12. Okay, let's say our real A is 12. So the point is that what is A right now in our code? A is going to be equal to, when the real A is 12, the A that we store in our code, we don't really know that it is 12. We just have it modulo mod. And our mod is 7. Yes, exactly. A will be 5 in our code. So we don't really know that it is 12. Even without knowing that it is 12, we want to see that what is that 12 divided by 3. Even without knowing what it is, we want to calculate it. So A is equal to 5. We want to divide it by 3. It says that instead of A divided by B, modulo mod, let's multiply it by B to the power of mod minus 1, because this is 1. And this is going to be equal to A times B to the power of mod minus 2. Let's see that what is B to the power of mod minus 2 and then multiply it by A. Okay, so what is B to the power of mod minus 2? It is going to be 3 to the power of 5. What is 3 to the power of 5? It's going to be 243, right? $243, I guess. I mean, because 245 is not divisible by 3. Yeah. So it's 243. So it says that instead of dividing by 3, let's multiply it by 243. So we have A times B to the power of mod minus 2. We want it modulo mod. We say that it is equal to A, which is 5, times 243. First, let's say that what do we expect? In here, we expect 4, right? The real answer is 4, right? We expect to have 4 at the end. But let's see what do we get. We expect to have 4. We have to multiply 5 by 243. What is that? What is 5 times 243? Is 1215. Is equal to 1215. And this time let's, instead of mod, really use 7. What is 1215 modulo 7? 1215 modulo 7. Let me share the screen. 1215 modulo 7 is gonna be equal to 4. So it is really equal to 4, exactly what we expected. Do you see it? So I even didn't know that it is 12. I just know that a modulo mod is 5. That's the only thing I used. And this is how I solved it. Now let's see that's where it is useful. One of the most important uses of Fermat is in calculating combinations. In combination. Let me explain it to you as well, and then I will also send you a problem that you can think about, and we might solve it in the next sessions as well. So assume that we want to use calculate combination. We want to see that what is n choose k. What really n choose k is? N choose k is equal to n factorial over k factorial n minus k factorial, right? Now the point is that this is where we see division. We can see that what n factorial is modulo mod. We can easily pre-compute the factorials of each numbers. We can have a 4 I equal to 0, I less than capital N, which is the maximum n that we need, I plus plus. We can just calculate the factorial of I. We can say that factorial of I is equal to 1LL times factorial of I minus 1 times I modulo mod. This way we can calculate the factorials of everything. And the point is that when you want to see that what is n choose k, you know n factorial modulo mod. You know k factorial modulo mod. And you know n minus k factorial modulo mod. But you don't know how to calculate the division, right? So the only issue in calculating combination is to how to calculate this division. This is the only thing that we need to in order to being able to calculate binomials, right? But now that we know Fermat, how can we do this? How can we use combination? Assume that you are given n and k, and you want to write that what is n choose k. How can you do that? You just need to do this division. N choose k is equal to n factorial over k factorial n minus k factorial. Exactly. We can just say that the answer is gonna be 1LL times factorial of n times inverse of factorial of k. We call b to the power of mod minus 2 as the inverse of b. This is inverse of b. Because it's like 1 over b. It is really 1 over b. But b to the power of mod minus 2, you can really look at it like 1 over b. It is something that if you multiply it by b, you will get 1. So you will calculate it by inverse of factorial of k, which is pw of factorial of k and mod minus 2 modulo mod, and then you multiply it by inverse of factorial of n minus k. modulo mod. So the point is that the only thing that we did was that for these two numbers, we raised them to the power of mod minus 2, and we multiplied them, and we calculated the answer modulo mod. And that's how we can calculate binomial coefficients. This way we can simply calculate all of them. I highly encourage you to try to implement it by yourself. Implement PW, implement power first, as we talked about, and then calculate factorials like this. And when you want to see that what is n choose k modulo some mod, just multiply factorial of n by PW of factorial of k and mod minus 2 by PW of factorial of n minus k and mod minus 2. In the next session, I can even code this for you. I can write the code and we can see that how it would be. Okay, thank you a lot, guys. There was also a problem that I wanted to tell you. I will send it to you and you can think about it. It has some good ideas as well, other than using a combination, etc. If you wanted, you can think about this. Thank you very much, guys. I'm so happy that if you understood everything. So you can also think about this problem and see that how we can solve them for the next session. Sure. How was today's session, guys? I mean, if you want to rate it from 0 to 10, how would you rate it? And feel free to rate it as you want. I mean, you can rate from 0 to 10. And I really use these numbers to decide to find that what are the issues and what we can change to make the next live streams better. So if you just answer honestly, that would be the best for me. You just can say if there was any issue, you can say that. Can you give me a number? I will also put a poll in our Telegram channel so that I should not open it right now. But I will also put a Telegram channel. In our Telegram channel, I will put a vote that you can also talk there about your rates. Sure, I will cover more problems on these topics as well. Sure. Thank you. Okay, if you wanted, feel free to join our Telegram channel as well. I will send you this is the link of our Telegram channel. This doesn't work. Let me. And as I said, every week we are going to talk about another topic. You can join the Telegram channel from this address. And for the next sessions, what do you want to be discussed? What do you guys prefer to be discussed? Do you prefer if we continue to talk about number theory, or you prefer if we talk about other topics? Combinatorics. Okay. Number theory and combinatorics. Number theory, sure. Especially we can have a session completely talking about Fermat. And we can even go over all these proofs in more detail as well. So, okay. Yes, we can also talk about more advanced topics as well. I mean, that's the main point. We are starting from easier topics and we will move on to more advanced topics gradually. So, I mean, over time we'll move on to more and more advanced topics. When we've covered basics, we're going to talk about more advanced topics. Yes, great. And thank you guys a lot for joining this live stream. Again, it was so great to see you. Sure, Centroid will be covered as well. It was great to see you in this topic stream. I hope that I can see you in the next topic streams as well. If you like this video, you can support my work by liking the video or subscribing to the channel, and also introducing these topic streams to your friends or other people who might not be aware of them yet. So if you know anyone who might also get benefits from these topic streams, it would be really nice if you can invite them to these topic streams as well. Thank you guys a lot. See you next time. Bye bye.